넘겨보겠습니다. 신준호 씨, 네. 이충아 씨, 네. 정상아 씨, 네. 그리고 배서령 씨, 그리고 최승주 씨, 네. 미스터 마니필, 김성수 씨. So unfortunately, it seems that the projector installed in this room does not work. But I have a little idea about how can I turn on this projector directly without using this system. So, okay, should you okay, so okay, can you see clearly? No? So then could you please move forward? Okay, so have your time. Please move forward. So we are close to the end of regulation. So this room has left for a while, almost about 2.5 years without any physical attendance. So I think that all of these fences are gone. But anyway, we have to live with it. Okay, so blue one survives, and usually red ones are gone. Okay, so if we if I remember correctly, from as of from May 2nd, we have no regulation about taking the distance between substances. So for example, here we have a certain empty position and empty position. So if you cannot clearly see this writing, then please move forward. And I will try to once again ask you the guys in the last row. Can you see it clearly? Okay. So what I strongly recommend you to move forward because you know that there will be no recording for this my writing on this whiteboard. So if you don't write correctly, then maybe this lecture content will be just gone without any recording. So okay, it's my really pity because I prepared some figures for you. So if you are interested with those figures, please visit our GitHub repository there. So there you can find the two figures. Actually, I think that we have to discuss about that those figures, because those figures are so important for our discussion. But anyway, we have to live with this situation. But hopefully, maybe in next week, May, so we will have a full recovery from the COVID-19 situation, at least in terms of school lecture or in college lecture. So I hope that maybe we will have a better facility for on offline lecture next week. Okay? So anyway, once again, sorry about this insufficient support for classroom. So today I have to live with this traditional way to write down something. Okay, we have spent already 10 minutes about this classroom settings. So anyway, I will try to my best to deliver the essential point. Okay, anyway, do you have any question about the lecture contents up to now? So still, although we have the poor environment right now, but it is still okay to have any question to me, so I can answer your question, even though our lecture progress is not that fast, but it's more important to answer your question than just to go me alone. Okay, so any question about? Okay, so then let's come back. But before starting our today's lecture, one student actually asked me to open the office hour, the online office hour. So according to his request, so I will open the online office hour in next Monday. So from 1 o'clock to 2 o'clock p.m. Of course, I think that this time slot is heavily occupied by other classes. So most of you have some other classes for this time slot. So you may say that, oh, I cannot attend it, although I'm very much interested. So if you have such a case, then please send me another email. So this offline lecture, or so online office hour was set by the request of one student. So all other students have the same privilege. So if you can send me an email, then I can open another online office hour. And of course, not only the student who asked me that request, so other students can join through our Zoom system. So let's discuss further about our lecture content and other. Okay. So this will be the first one. So please feel free to ask me another time slot. Of course, I have also busy schedule, so we have to make some negotiation about the time slot available for both of us, me and you. But anyway, so I can provide multiple time slots for you. So please ask me the office hour, online office hour. I prefer to have the online office hour. Okay, so then let's come back to our main lecture content. So where are we now? So if we have some axis starting from the March, and this is maybe around the final examination. So maybe we are around just the middle of our lecture. So you have already done your midterm examination. So up to now, quite close to the last lecture, you have spent a lot of time about understanding on PN junction and basic knowledge on the analysis of electronic circuit was discussed in this period. However, as I stressed in the previous lecture, actually PN junction is not the most widely used or most important type of semiconductor device or circuit element. The most important one will be discussed, and its name is MOSFET. And the previous lecture, lecture 14, was devoted to the first structure called MOS. So I'm planning to have 2 more classes for this device, and this is the second time for discussing about this type called MOSFET. So lecture 14. So we have thought about how about the behavior of MOS system, and today we'll further continue the discussion about this MOS structure, and at the second half of our lecture we will try to introduce certain information about how can you use it as a transistor. So that concept will be discussed, and next Monday we will have more quantitatively or qualitatively discuss about the behavior of our MOSFET. So, for example, IV characteristics of this device will be discussed. Okay, so this is lecture 14. Now we are at 15 and 16. Then more or less we will have about 10 more lectures about our semester. Then what will happen? So from that point, we'll try to introduce some very simple but very fundamental sub-circuit which can be used to understand the behavior of our digital system, at the same time analog system. So that will be the lecture progress for our remaining semester. Okay? Do you have any question about this lecture progress? Still, you can ask me any question about this one or that one, or your future, about what will be discussed in this part of now. Okay? So please interrupt me anytime. So if you don't have any question, then now let's directly jump into lecture 15 about continued discussion about MOS structure, and let's go to the second part, the concept of field effect transistor. Okay, so then let me just start from our review on lecture 14. Yes, so we have discussed about the MOS structure. The first half was devoted to what is the MOS structure, and now you understand, although we say MOS, but it contains a lot of story behind it. For example, this metal, previously it was, at the beginning it was metal, and later it became polysilicon. Oh, so sorry about that, you cannot see it clearly, but so I have to write down more clearly. Polycrystalline silicon was used. After that, now once again we are now using metal and oxide. That is really pure silicon dioxide in a former time. However, in nowadays we are using some composite layer of insulating materials like silicon dioxide as an intermediate layer, and also hafnium oxide will be used as the high K metal gate stack. So anyway, and here we have a silicon. Yes, silicon. It is still silicon, and sometimes I want to say that for a long time is that more than several decades, we have used silicon. But you know, from just a few years ago, actually, we are no longer using pure silicon as a channel material. Have you heard about that? So already we have moved to another era. That, so nowadays, in the channel of our transistor, we are currently using silicon germanium. So you know silicon, and germanium is another group 14 element which has a lower atomic number than silicon, and they are combined, so they can make a compound. Or actually they are not called as a compound, so they are called as a alloy. So both of them are belonging to group 14. So just not like gallium arsenide. This is corresponding to group number 13 and 15. Yes, in this case we call it as a compound semiconductor. They are belonging to the same group, so typically we call it as alloy. But anyway, point is, we have introduced a lot of changes during the last several decades. So MOS system, the basic philosophy is given. However, people, engineers in the industry has continuously makes some innovations about the material composition. Why? In order to achieve maximum performance available at the time. So at the time, every time they did their best, and if they have another means to improve the performance, they switch it to another configuration. So then what will be our lecture? So in our lecture, we just consider the combination like metal, pure silicon oxide, and pure silicon. So is it really a old-fashioned technology? Yes. However, don't worry about that. The basic physics inside it is the same, and the difference only comes from the most advanced technology. So once you understand this combination, then you can just understand other combinations by simply adding some more facts on those components. So please just go with the most traditional one, like metal is metal, and silicon dioxide is this oxide layer, and we are now using pure silicon. Okay, do you have any question? So that was the review of the first part of lecture 14, but that was the structural description about the structure. Yes, we have MOS, and the most significant thickness length scale is that of this guy. Yes, so this is the most important scale in a vertical direction of our MOS, because usually this silicon is regarded as infinitely long, and also metal, since this is too highly conductive, so whether this is short or long doesn't make any difference in its conductance. So most important thing is this one, and here we introduce certain symbols like this, T-ox. So what is T-ox is thickness of oxide layer. and its value would be nowadays just nanometer scale. So nanometer scale. So if you just to open the graphs in our GitHub repository, you will find that my example graph. So I have drawn some certain figures, and that contains the result of 45 angstrom thick one. So 45 angstrom means that this is just 4.5 nanometer. So from the viewpoint of our current technology, so this is a somewhat old one. So this is very thick oxide inside it. So of course we can reduce it by introducing further scaled technology. But anyway, when we start our technology, this value 4.5 was not achievable. So previously it was even thicker than 10 nanometer, much thicker than that. And one student asked me a very good question about that. So I in the last lecture I told you that the controlling this T-ox is critically important. Yes, that is important. Then who decide the minimum variation of this T-ox? Oxide thickness is defined as the point where we have silicon and silicon dioxide and ends up the top point where our silicon oxide ends, and now we have to deposit the metal on top of it. Okay, so are you with me? So this thickness is corresponding to T-ox, and this is really silicon dioxide, and whether it ends here or whether it ends here, that is determined by what? So whether we have one additional layer of silicon dioxide or not. That determines the thickness variation. However, this difference is just orders of 0 point something nanometer scale. So if we have one additional layer or not, it just changes a few angstrom scale size. So if our overall thickness is, for example, 10 nanometer, and say that you have just introduced for example, 0.1 nanometer difference, then maybe that doesn't make much difference because the thickness is just 10 and changing a little bit doesn't matter. But think about this one. Now we have scaled this system tremendously. So now we have just please, there is no such thing like a really 1 nanometer thick oxide layer, electrically 1 nanometer thick oxide layer. But anyway, if we have such kind of thin, extremely thin oxide layer, then what will happen? If we have same amount of variation, thickness variation, but that will be felt as really tremendous variation for its thickness. Okay, so since the average value is scaled down tremendously, so we have more severe condition for controlling the thickness of this system. But have you already done the homework in the previous lecture? We had only one single problem, and the question was calculate the capacitance originated from your oxide layer, and the answer would be quite easy. So you have to consider the relative permittivity of your silicon dioxide 3.9, and you have permittivity of vacuum, and here you will have per, yes, so you have sorry, not D in this case, oxide thickness. So if you have 10 times thinner oxide layer, then what will happen? Your COX value will be 10 times higher. And if you have 10 times a thicker one, so instead of 1 nanometer, if you introduce 10 nanometer thick layer, it means that your capacitance will be drastically reduced by a factor of 0.1. Okay, so simply speaking, if you have, let's say, you have same silicon, yes, here you have the same silicon, and you introduce here 10 nanometer thick oxide layer, and you introduce just 1 nanometer thick oxide layer. Then from the viewpoint of electrical coupling between this guy and metal, and this guy and metal, this silicon and metal are capacitively coupling by this oxide layer. And here, once again, metal and silicon are capacitively coupled by this oxide layer. Then what will be the strong connection between this left one and right one? Obviously, you can say that this guy has much strong coupling between our silicon substrate and metal. So are you with me? Because here we have a really thin oxide layer, and its COX value is 10 times higher than COX value of this guy. So the coupling, electrical coupling through the capacitance will be 10 times higher. So it means that if you try to, for example, let's say that you have applied a certain voltage. So like this. For example, let's say that you have applied 0.7 volt and 0.7 volt. And what you do usually is just to increase additional voltage. And you want to increase additional voltage and try to what happens to these two structures. So they have relatively weak coupling, and this guy has a relatively strong coupling. Then what will happen? You know, now we are considering two different systems. Here we have metal, silicon, and this is COX, and here we have 10 times COX. Okay, so let's say that this one, the left one, is labeled as a COX user, and this one is 10 times larger value, has the 10 times larger value. Why? We have 10 times thinner oxide layer. Then let's say that we have applied additional voltage called or written as delta V. So here I have applied additional voltage delta V and delta V. Same amount of additional voltage is applied to both of this left structure and right structure. Then what will happen? What we wanted to calculate is take the charge further collected by this additional voltage. Then who decide which component decide the amount of charge? Maybe you remember that the charge collected across the parallel plate, two parallel metal plates, is given by capacitance multiplied by the voltage difference. But here, from the virtue of our assumption, we have applied the same amount of voltage difference, additional voltage difference, So we can say that this is the same. Then what will be the difference? Only this difference in capacitance will determine the amount of charge collected the silicon layer. So now you can easily understand the additional amount of charge collected here, negative charge, will be given by Cox times delta V. You will have this additional amount of charge here. And here, if we are looking at this part, then what will be the value? You will have 10 times larger amount of charge collected by your same amount of voltage change. So, wow, what happens? So think about this one. Now we have this balance like this, and I just change it by 1 centimeter. So let's say that this is a fixed, and I just change it by 1 centimeter. Then this guy will move. Then if they are really perfectly balanced, then what will happen? If I move it by amount of 1 centimeter, then this one will go up by 1 centimeter. However, instead of that, let's assume that I'm using this guy, and I fix it here, and also changing only 1 centimeter. Then what will happen? Since the distance between this fixed point and the end of our load are different, this is short and this is long. Although I change it slightly, only 1 centimeter here, however, the movement of this part will be much larger than just, or much longer than 1 centimeter. So, quite similarly, here we have applied the same amount of additional voltage. However, the behavior of this right one, which has a larger capacitance, is much more desirable for us, because we wanted to just to make our system completely quite much charge, quite much heavy charge, or almost no charge by amount of small voltage change. Okay, so this one becomes a really sensitive one for your voltage difference, and here this guy becomes relatively insensitive one. So for your voltage difference, then which one is, from the viewpoint of your engineering, what will be the preference? So okay, I want to live with this small CX case. No, this is not the case. Always people love to have higher and higher capacitance. Okay, because it means that just to change a little bit your metal voltage, or sometimes called as, more frequently called as gate voltage, you can collect a lot of charges. So means that, think about this case. Let's say that there is a minimum amount of charge you wanted to have to operate your system. So obviously, at the beginning, you have almost no charge in it. And by applying additional voltage, you have to collect your charge across the oxide layer. Let's say that this. Then, if this bar is just given as a fixed, then which one will require smaller voltage for achieve this goal? If our goal is arrive at a certain amount of charge, then this guy will require really small amount of operation voltage, and this one will require much more. So simply speaking, with this highest COX capacitance, so which means that really thin oxide, then you can get much more charges across the system. Okay, do you have any question about my explanation? So starting from the review of our previous lecture, last lecture L14, so we are now talking about the importance of COX. And the COX, if you have a higher COX, that will be great for your application. And who decide the COX? Actually, thickness really determines the COX. So we have to use thinner and thinner oxide thickness. So, but you know, yes, I love to have a thinner one. So make it just half, or make it just one third. That doesn't make sense because reducing the thickness of oxide makes a lot of difficult problems. So people never do it aggressively. So slightly reduce it and test it, and if it works, then and after that, several years later, they can also slightly reduce it further, and continuously improve the amount of their oxide capacitance. Okay, so this was the first one, and let's go to the second part of our lecture 14. So now we have this MOS system, and let's assume that this silicon is made of P-type silicon. And if we have a P-type silicon, if we don't have any kind of surface effect, then usually what we can expect is inside it we have a lot of mobile holes. Yes, there are tons of holes, and also same amount of negatively charged atomic cores are there. So if you have any question, then please interrupt me anytime. So if we think just naively, then we can say that the number of holes, positively charged holes, and number of acceptors which are negatively charged, they are perfectly, so usually this H, the alphabet H, is not the universal symbol for hole density. Usually for hole density, we prefer to use just alphabet P. But anyway, just regard my notation as for just a simple explanation. Don't treat it as a universal notation. So once again, the universal symbol for hole density should be P. Okay. So anyway, the number of positively charged holes and number of negatively charged acceptor atoms are the same. So that will be the usual thinking about this P-type substrate. However, point is, this is not just a P-type substrate. Here we have a strong surface effect. So which surface effect means that we have introduced the extremely thin oxide layer and deposit a metal layer, and this metal has highly biased. Highly biased means that sometimes we can apply 0.7 volt, or sometimes even larger volt, or sometimes we can apply even negative volt or 0 volt. Any kind of voltage can be applied. So in this case, we cannot assume that this status of this silicon substrate is the same with just a bulk system. So bulk system means that the system without any surface characteristics. Just to, if you make just a large system where the surface doesn't play any important role, then we call it as a bulk. But in this case, this is really surface dominated system, and since we have applied certain voltage, and here we have also applied another voltage, we will have strong electric field. Oh, sorry about that. I have this noise. So we have strong electric field across the oxide layer, and this additional oxide layer, this strong oxide, oh sorry about that, strong electric field should be compensated by the motion of our charged carrier here. So if we just magnify once again, then can you see clearly? So manually. So here we have oxide, and here we have silicon, and we have a lot of holes here, and now we have a strong electric field. And in order to compensate this electric field, and let's say that in order to make it small, strong one is comes in and weaker one is comes out. This condition can be only achieved by the net charge density, which should be negative. So maybe you understand. From the viewpoint of Coulomb's law, if you have positive charge at a certain position, then you can draw the field line. How does the field line look like? If you have positive charge, then you will have a certain outgoing field line. And think about this one. If you have a negative charge, then how does it look like? Yes, fields are comes in. Yes. So think about this one. If you have really a positive charge, then your field line should look like this. This arrow should be larger than this arrow. So we can have overall the outgoing flux. However, since we wanted to have almost diminishing electric field deep inside our p-type substrate, so point is we have to introduce negative sign, negative charges overall. So we have to anyhow find out the physical mechanisms to provide negative charges. But what was the result, or what was the conclusion of our previous lecture? The previous lecture is, in the case of this p-type substrate, they have mobile carrier and they have immobile atomic cores. And this guy cannot move, and this guy can move. So by removing holes from the surface layer, we can generate a layer of negatively charged position. So now you can understand. In order to make our electric field almost close to zero, so this p-type substrate just to behave like this. To here, this is just to neutral. Neutral means that the number of holes here is almost identical to that of acceptor atoms. However, in this part, so now we can say that hole density would be quite close to zero, and of course Na minus, that is not zero at all. This is just given as a certain number, like 10 to the 17 per cubic centimeter, 10 to the 19 per cubic centimeter. This number is just given. So overall, we will find that here the net charge is given by minus Q. Minus Q is the elemental charge of our negatively charged particle, and here multiply Na minus. That will be the point-wise charge density. So the unit will be of course Coulomb per unit volume. So of course we can, when we integrate our point-wise charge density across this axis, yes, then we will have one additional length scale. Then eventually we will have something like a Coulomb per square centimeter. So here square centimeter is from the top view. From the top of our wafer, we can think about a unit area and how many charges are there. The amount of charge is collected by this number. Okay. Any questions? So I think that was the second part of our previous lecture 14. So we have spent already 40 minutes about reviewing the the previous lecture, but I think that is really important. So now only when you understand this previous lecture contents, then now we can move into the most important topic I want to deliver in today's lecture. Okay. So now you understand. Oh, okay. Before starting my main lecture, so do you have any question about the review process? So if you have any question, then please let me know. Then if this system just behave like this, then that will not be very useful for our application. Think about a certain status. So now we have, yes, now we have a certain layer. Okay, here. This layer is perfectly negatively charged. However, if we just break down this negatively charged layer into its components, then we can find that although they are negatively charged, but this is not related with electrons. There is almost no electrons at all. Instead of that, here we have always immobile ionized atoms. That is the situation. Oh, so we can ask ourselves about this question. So then, yes, anyhow we succeed to collect certain negative charges. Then, how many mobile carriers are there? Mobile carriers will be used for transistor operation. However, if we have a look at this system, this means that nothing, no available mobile carriers. So at the end of our previous lecture, one student came to me and asked me that question. If we cannot use any, cannot find any carrier, then is it good for our application? So although we spent almost 40 or 50 minutes on explaining the behavior of this system, the MOS system, what we get from up to now is this one is useless. We cannot collect the mobile charges. Although we have negative charges, but they are not mobile. They cannot move. They do not conduct. They do not conduct the current. So, but I think that question is really important. this one? Yes, at first glance, it sounds really disappointing. Although we have applied a certain voltage, we do not get any kind of meaningful number of charges, mobile charges. So that sounds quite disappointing, but that is the real beauty of this system. I mean that. Let's think about this one. So I think that we are now getting close to the main message of today's lecture. Let's say that this is the axis corresponding to metal voltage. However, instead of metal voltage, usually we prefer to have a term like gate voltage. So because this metal usually called as gate or gate, so we have to write down gate voltage. Then what we can expect is, so if this axis becomes so number of sorry about that. So let me just have time to calm down. So if I just introduce negatively charged density, the number of negative charge or density of negative charge, so let's say the coulomb per square centimeter. So please look at this is a negative. So because all of charge considered in our consideration are negative, however negative is not that convenient to draw in this upper part, so intentionally I say negatively charged particle. Then think about this one. If you look at the graphs attached to or posted in our GitHub repository, now you can find the charge calculated by computer. So at the beginning, when you apply 0 volt, now you have a certain non-zero amount of negatively charged particle. Okay? And this, what is this guy? Is this mobile or immobile? So this is just a fixed charge that doesn't move at all. Then what will happen? If we increase further and further the gate voltage, then what will happen to this guy? Since we have applied even higher voltage, we will have even stronger electric field. So our system, this p-type substrate, should provide more negatively charged layer. So it will increase this point. So move back, move back, move back. So if we draw this behavior, then you can find that there is a quite moderate behavior with respect to the gate voltage. We apply additional voltage, so we have additional charge. Okay, so this graph is really corresponding to, if I increase the gate voltage a little bit, then how much we will have additionally? Yes, this difference is corresponding to the additional amount of charge collected by this p-type substrate. So are you with me? So of course it is not like this. So maybe you will be very happy if we have something like this. If we have something like this, charge versus gate, that looks like a straight line penetrating the origin, then maybe you will love it. But this is just a linear capacitor. When you apply 0 volt, then there is no charge. And yes, you know it. This is simply given by Q times CV graph. However, our MOS system does not behave not like this. Why? It has different substrate. Substrate is no longer a metal, but that has the p-type type silicon. So that's the reason why its behavior is much different from that of our usual capacitor. But anyhow, you can find that if we apply additional voltage, then we have additional charge, and if we have additional voltage and additional charge, that is the situation. Okay. Any question about drawing these graphs? So it's my pity because I have prepared really beautiful graphs for our today's lecture, but so please, I wanted to recommend you that just to visit our GitHub repository, and you will find much more clearer graphs for this guy. But anyway, my point is, yes, how many mobile charges? Nothing. How many mobile charges? Nothing. So if everything goes like this, then we cannot use this system for our application. But point is, amazingly, at a certain voltage, which is far from just 0 volt, there you find certain deviation from this blue graph. So let me just draw it. Yes, so what I wanted to say is actually the overall behavior of negative charge collected at silicon substrate just looks like this. It just follows our previous description. After that, beyond a certain voltage, we have no idea about what is this exactly, but anyhow there exists certain voltage, and beyond this level, now we can find certain deviation from the behavior, this blue color. What was this blue color? This blue colored line was originated from the mechanism of depletion of holes. Holes are depleted from the surface, and if we apply larger bias voltage, then more holes will be depleted. That is the physical origin of this behavior. However, the realistic one have strong deviation from this blue colored curve. So it means that we need to introduce additional mechanism to explain this behavior. What is it? So that is the main point of our today's lecture, and the answer is, okay, up to now we have provided the required negative charge by the depletion of holes, but if our gate voltage, once again the gate voltage means that the voltage applied to our top metal, if the voltage is beyond certain amount, so we have no idea, but if we apply gate voltage larger or higher than certain number, then we have the second mechanism to provide negatively charged particles. What is it? That's the point. That strongly makes this difference. What is it? So what can be the negative charge? Of course, non-existence of holes or non-existence of positively charged can be interpreted as net negative charge. However, why don't we just introduce a real negative charge? Then which one has the real negative charge? So you know, electrons has really negative charge. Or electron itself has negatively charged. And if we have donors, then donors are positively charged. So if we can remove donor out of our system, then we will have also negative charge. However, please remember that we are now talking about p-type substrate, so there is no donors at all. Then the only available possibility is electrons. So simply speaking, in order to explain of this behavior, we have to assume that, okay, as a second mechanism, if we apply too high voltage to our gate, then we will directly collect electrons. That's the point. So if we draw, so let me just draw one graph here. Let's just say that this axis is corresponding to the density of negatively charged particle, and let's say that this vertical axis is corresponding to the depth direction. So this is corresponding to the interface, and if we goes down, then we are now approaching to the deep substrate. Then if we don't care about these electrons, then how does it look like? Up to this point, we will have a negatively charged layer. Yes, there will be negatively charged layer, and physical origin is comes from, yes, negatively charged acceptors. That is the situation when we consider this depleted whole layer. So this is a depletion layer. However, if we consider this second mechanism, electrons, then in addition to this negatively charged layer due to the depletion layer, we will introduce another contribution from electrons. That's the point. Yes. Now you can understand the behavior of your MOS capacitor like this. Up to certain voltage, let's just call it as threshold voltage. Threshold means that where is the threshold? We don't have a threshold here, but in your home, you have many threshold. Threshold means that a small structure which makes the distinction between your living room and your sleeping room or your study room. There is a small bump, and this is corresponding to threshold. So this is a threshold, and yes, we just introduce a quantity called threshold, and if your bias voltage, gate voltage, is beyond the threshold voltage, then now you can collect electrons, and that perfectly fits for your application, your purpose. What is it? So now you have really mobile carriers. These guys can be used for your electronic purpose. By using this guy, you can conduct and just insulate the channel or the device circuit element. Okay? So are you with me? In some sense, this guy is useless for your electrical conduction, and this guy is useful for your electrical conduction. So, do you have any question? So I think that this is a really important one. The existence of electronic layer, which is formulated when the metal voltage is higher than threshold voltage. That is the main concept you have to keep in mind in this lecture. Okay? Of course, you can ask me this question: how can you justify the existence of this electron layer? But that is the question I wanted to avoid until by next semester. So if you are interested, please attend the course for the semiconductor materials and devices. So it is only because we have omitted so many discussions about band structure or something like that. So this is more closely related to the band structure of silicon or band diagram. So I just make it just introductory. So, but let me just give you some certain description. Think about this one. Voltage is larger than threshold voltage, and threshold voltage is usually positive number. So this one really high voltage. Then it try to persuade negative charges and try to collect someone. Then we need negative charge, but here, as you can see, our front for hole depletion is located here. If we apply further and further voltage, then this front moves away. So if we apply high enough voltage, actually, although we have a strong electric field, it becomes more and more inefficient to collect additional negative charge by action of this depletion. So it is because like this. Here we have a certain guy to manipulate. Yes, it can be easily manipulated. However, if that is located far away, then it becomes really difficult for me to manipulate. Something like this. Here, if we have a sufficiently large electric field, then already our depletion layer goes deep into the substrate, so it becomes more and more inefficient to change it. But now, since there is a strong, really strong electric field, so electrons, which is located here, feel it. So more exactly, here at the edge of our depletion layer, once it is just to come into this part, then what will happen? Because here we have a strong electric field, yes, there will be certain clip for our electrons. If some unlucky electron just comes into this depletion layer, then it will be immediately collected to this position. So that is some description about why we have additional electron layer generated from this structure. But anyway, this behavior or this phenomenon is called as, please remember this name, this phenomenon is called as inversion. Please remember this word. Inversion means that to the pioneers in this electronics, they thought that we have doped our silicon with p-type. So the usual expectation is we wanted to find out holes inside it. However, by applying such kind of surface effect, so we intentionally makes what? We intentionally makes electrons. Oh, electrons can be found in the n-type substrate. However, even though we have a p-type substrate, using the surface effect, we generated the electrons. So to them, so our ancestors, they thought that, oh, it's like a type inversion. Although its physical type was p-type, but it behaves just like a type is inverted into n-type. So that's the reason why they call it as inversion. But anyhow, okay, that is just the historical one. But that is the universal name for describing this behavior. So now you can understand. So beyond this threshold voltage, although we have negative charge, but that negative charge is useless for our transport or electronic purpose. And beyond the threshold voltage, now we can get some electrons which can be used for our electrical conduction. So are you with me? So this is the most important message I wanted to deliver in this today's lecture. And here goes my final question. If you all of you have understood up to now, the natural question is to some guys who are just a newcomer in this field, it seems like this reason, this operational reason seems to be redundant. So are you with me? So it means that from 0 up to threshold voltage, although we applied gate voltage, however, we just collected nothing. We have no electrons at all. So this amount of voltage seems to be wasted. That is the usual thinking of the first comer. However, I wanted to stress that no, the existence of this margin, voltage margin, is the real beauty of our transistor. It means that if we have almost the vanishing threshold voltage, let's say that even at 0 voltage, let's say we have already electrons there. It means that if we have such a case, then let me just write down my last sentence in this lecture. If we have 0 threshold voltage, then we cannot turn without the positive value of threshold voltage. We never turn the transistor off. So please remember that what is the purpose of, or what is the role of a transistor? What is a device? That should work as an electrical switch. However, if we don't have this voltage margin, then even when we apply 0 voltage, this one conduct, and every time switch is on. That is not the case we wanted to have. We certainly have make a clear distinction between off state and on state. So we have to have reasonable value of threshold voltage. Okay. So I think that the time is up. So we have to stop now. But if you have any further questions, then please send me an email, or yes, we will have also another office hour next Monday. Thank you, and I will try to fix this problem next